stuff to begin with. Hopefully someone joins in as well, a real human. If there's no human, there's a human replacement. So if we're turning it later into a video, we have to cut the beginning out. Let me just share this on socials just in case someone wants to join in. I had to get the link. I had to start streaming to get the stream link. And we're also pretty much on every social under the sky. Well, some of them were using more than others. We're using more LinkedIn. Haven't been using TikTok in a while. Might be actually shut soon or something. I don't know what's up. All the politicking. TikToking. Yeah, we have a Facebook group. We mainly post and run. Post and run. We're on Reddit as well. Can share links. Let's try it out. Not sure why I'm doing this manually. There really should be an agent doing this for me, isn't there? Sometimes this platform's changing the links, which is a bit annoying. Okay, I'll start in a sec. Do I have an internet outage or something? No, I'm not sure what's up. Hey, give me a sec. Yeah, really have to remember getting rid of it later. Especially if we're editing this into a standalone video. Really have to get rid of all this stuff in the beginning. Yeah, it's changing the links, removing the links and things like that. Wait a sec. Yeah, this will be boring, yes, but if you have any questions about the site, everything we do is available on biomedical.com. You can sort it out by features, tools. This is the, producer favorite. Yeah, TikTok is annoying. What's the TikTok? I don't even know which one is which. X, whatever. Twitter is annoying that way. Because it has character limits. That's not fun. Yeah, Blue Sky is essentially trying to be the same as the X, whatever. I don't use either, neither, neither. Can we have everything automated? I mean, we can also do the whole stream automated. If I need a break, you just have this. Yeah, the notebook LM is pretty good. We're doing this live stream developing a website run biomedical data applications. If you know anything about it, do let me know. But yeah, if you can. Oops, having some issues with the sound. Wait a sec. Issues with the sound. Okay, now we're back. Wait a sec, can you just speak more casually? Can you do like an Eastern European accent and pretend being like a 21-year-old so we don't lose our audience? Make it sharp and witty. If you keen to be fun, go for it. But yeah, can you give us an overview? And are you happy to live stream together? Are you happy to host this live stream on YouTube?
All right, let's keep it casual and fun. Imagine me as a sharp, witty 21-year-old from Eastern Europe, ready to dive into this live stream. Hosting a website for medical data? No problem. We'll focus on making sure everything's secure, compliant, and user-friendly. And
Yeah,
I'm
forget about that. Yeah. The voice, the voice is okay, but just get rid of any fluff, get straight to the point. We are not worried about security at this stage. We're doing an open source project.
Got it. Straight to the point. If security isn't the main concern right now and it's open source, then let's zero in on functionality, performance, and collaboration. You'll want to focus on a clean modular code base so contributors can easily dump in. Documentation is crucial so new devs can get up to speed quickly. Make sure the architecture is scalable and flexible, and leverage popular frameworks to attract more developers. Plus, a clear roadmap and active community engagement will keep the momentum going. Let's make it efficient and welcoming for everyone who wants to contribute.
Yeah, don't like it anymore. Don't like it. Let's actually move on to Notebook 11. It seems to be better. And yes, we will jump into development and at some stage. Sorry for the birds. The birds are going crazy. Let's see if Soar can follow basic instructions. I actually made so this is all the stuff that we are covering. I actually had like a model selection thingy. Yeah, model selector. Yeah, eventually we're trying to get something that just works. Let's actually look at the code quickly. Open the AI model T matrix. Because that's kind of important. Don't understand what are you doing. Yeah, we had like a thumbnail for the video, but we also need a thumbnail for the tool itself. So we have this human body simulation thingy. If it stance. Yeah, because originally it had this slider and this coordinate, which we don't particularly like. We have a couple of the SVGs empty at the moment. Might need it in a separate project. So we are not doing editing yet. Yeah, there is this slopification going on. It's making those images more and more generic every time you ask to change something. Yeah, it's slopified the body as well. Yeah, actually, let's do the notebook LM first. This will be a standalone thing around 11 minutes. And we can try the interactive mode as well. So we added like a YouTube video, the whole website, the specific tool, the CardioBot. We're talking about CardioBot. It's what it looks like at the moment. Again, we have two hosts. We'll be talking about it, and we can supposedly intervene just in case something goes wrong or they start hallucinating too much.
AI, it's turning up everywhere, isn't it? But today we're doing the deep dive into something pretty vital. how it's being used to analyze ECG waveforms, like in real time.
Right.
And if you're anything like me, always wanting to, really get the technical details, but quickly without getting totally bogged down, I think you'll find this interesting.
Absolutely. And we've got some really great material to work with here. It digs into the mechanics, the implications. It's quite fascinating, actually.
Exactly. So our mission, let's call it, is to explore the nuts and bolts, how AI can spot those critical ECG abnormalities right when they happen.
Mm-hmm.
We want to understand the tech, see the potential, but also, take a really honest look at where it's maybe not quite there yet.
Yeah, where it falls short.
And knowing you like to understand the how and the why, we're aiming to make this deep dive really insightful and, well, maybe even a bit fun.
Sounds like a plan. So resource-wise, we've got a few things. There's a transcript from a YouTube channel, Bionic Chaos, kind of an experimental, hands-on look.
Okay?
Then we'll look at the Bionic Chaos website itself, their biomedical data tools and resources page, give a broader picture.
Right.
And finally, some details on something called the CardioBot ECG Analysis Challenge, which sort of tests this AI.
Okay, cool. Let's start with that Bionic Chaos YouTube video then. But what jumped out at me was how experimental it felt.
Hmm.
They even mentioned using ChatGPT just to like whip up a bland Altman plot.
Oh, interesting.
Yeah. And for anyone wondering, the Bionic Chaos site explains those plots are for comparing measurement techniques, like seeing if one method reads higher or lower than another. They use EEG analysis as an example on the site.
Right, comparing two methods.
So seeing it in the video, even AI generated, it really shows this sort of investigative, let's try this mindset.
That's a great point. It shows they're even using AI to help visualize the output of their AI tools. But the main thing in the video really is the real-time analysis aspect,
Yeah, absolutely. It's about spotting problems now.
not digging through old files.
And to really, push the system, they showed adding noise between the waveforms,
Okay.
not messing with the heart signal itself, but the gaps. Seemed like a smart way to simulate, I don't know, real-world interference. See how the AI holds up.
Exactly. That controlled noise injection is, well, it's essential for checking reliability, isn't it? Especially for algorithms like this.
Uh-huh.
You see how it reacts to different noise levels, you start to understand its limits, how easily it might get confused by messy signals.
And here's where it got really interesting, or maybe concerning. The video shows the AI, the robot, actually messing up.
Oh.
Yeah, like there was a false alarm when the noise was cranked right up, and then a bit later, it completely missed an abnormal waveform, just didn't flag it.
Wow, okay, that's a critical finding. It really underscores that these systems, even advanced ones, they aren't perfect.
Right.
A false alarm, that means unnecessary tests, patient anxiety maybe, but a missed abnormality, that could be serious. Delayed diagnosis, delayed treatment.
Big consequences. And the video also brought up this cardiobot game.
Ah, yes, the competition.
Yeah, where a human tries to beat the AI at spotting bad ECGs. The creator noted the machine often wins, which, okay, that makes you think.
It does.
But then they raised the issue of human distraction, painted this scenario where maybe a human analyst just looks away for a second and misses something crucial.
That highlights a potential strength of automation, doesn't it? Consistency, vigilance. AI doesn't get tired or distracted like we do.
True.
But as we just heard, it has its own failure modes, like that false alarm or the missed beat. Different problems, but still problems.
And right at the end, they hinted at looking into neural networks next. So it seems they're exploring different AI approaches too.
That's definitely worth noting, because fuzzy logic, which we'll get into, is one way. Neural networks are another beast entirely.
Right.
They learn patterns from huge data sets, which could be really powerful for something as complex as ECGs. They might spot things fuzzy logic rules wouldn't.
Okay, so let's shift gears then. Talk more about the Bionic Chaos website and this cardiobot thing. It's set up like an actual game, right? You versus the robot.
Exactly, an interactive ECG scoring game. And the basic idea is pretty simple, but actually quite clever for learning.
How's it work?
You see ECG waveforms scrolling by, you click the abnormal ones, ignore the normal ones, get points for being right, lose points for being wrong.
Okay, simple enough. But how does the robot do its part? That's the interesting bit.
It is. The website says it uses a Python-based fuzzy logic system.
Fuzzy logic. Okay, break that down a bit.
So think of it like this. Instead of just saying yes or no, normal or abnormal, fuzzy logic deals in degrees. Sort of abnormal, very likely normal, that kind of thing.
Ah, like shades of gray.
Precisely. Which is really useful for biological signals because they're messy, variable, it's not always black and white.
Makes sense.
So this cardiobot robot looks at things like um, frequency, amplitude, the shape of the peaks, but here's the kicker. It does this without knowing beforehand which waveforms are good or bad.
No labels.
Really, how?
It works based on the fuzzy rules it's been given. It assesses the characteristics in real time and makes a judgment based on those rules.
Wow. So playing the game, comparing your score, you're literally pinning your human intuition against this fuzzy logic system.
Yeah, it's a direct comparison, a great way to get a feel for it, and maybe even benchmark your own skills, like you said.
And that ties right back to the video, that real-time analysis demo. CardioBot lets you kind of experience the challenge firsthand.
Definitely. The website suggests it's both for learning and benchmarking.
And looking around the Bionic Chaos site, there's loads of other cool stuff too, like myoscope for muscle signals, EMG,
I saw that.
Pulsaviz for heart rate graphs, an E-waveform simulator. It really feels like the creator wants to make this complex biomedical stuff more interactive, maybe even fun.
I think that's exactly the aim. You see it on other tools too, like the hearing aid simulator or SpectroWave. They encourage you to play around to engage actively with the data, not just read about it.
Which could be way more effective for learning, right?
Absolutely.
Okay, so let's dig into the more critical side again. We talk about fuzzy logic, dealing with ambiguity. But those AI errors in the video, the false positive, the missed beat, what are the real-world consequences we need to think about?
Well, they're significant, as we touched on. A false positive isn't just an oops. It can trigger a cascade of further tests, maybe invasive procedures, not to mention patient anxiety. It costs time, money, emotional toll.
Right.
And the missed beat, the false negative, that's potentially even worse. A patient might have a serious condition that goes undetected, treatment gets delayed, the outcome could be much poorer.
So it's this balancing act, finding problems without crying wolf too
There's
often.
a hooked human
Exactly.
in
It's
the
about
room, by the way.
sensitivity catching the
Do you
real
have any
problems
questions?
versus specificity correctly identifying the normal cases. Tuning an AI to do both well, especially with noisy variable data like ECGs, is a huge challenge.
And the CardioBot description even says it's hard, distinguishing normal from abnormal patterns, even for humans.
It really is. ECGs vary a lot between people, even in the same person day to day. Spotting those subtle, critical changes takes expertise.
Uh-huh.
AI can analyze quantitative stuff like frequency really consistently, which is good, but it needs to be smart enough or trained well enough to understand the huge range of normal and not just flag every tiny deviation while still catching the truly significant abnormalities.
So what about that disclaimer on Bionic Chaos site? It says pretty clearly it's all experimental for education and research, not clinical use.
Yeah, that disclaimer is key context.
What does it tell us?
It tells us these tools are still firmly in the development and exploration stage. They're great for learning, for research, maybe for proving concepts, but they are absolutely not ready for doctors to rely on for making patient diagnoses. Not yet.
Right. Needs way more testing, validation.
Huge amounts on large, diverse patient groups, plus regulatory hurdles, ethical considerations. There's a long road before something like this sees routine clinical use.
Still, it's interesting. They list a tool for EG monitoring in ICU on the site. That idea of real-time analysis feels like it has potential in critical care beyond just ECGs.
Oh, absolutely. Continuous monitoring in the ICU. Imagine an AI constantly watching EEG, ECG, other vital signs, flagging subtle changes before a human might notice, potentially alerting staff to a developing crisis much earlier.
Yeah, that could be huge.
The core idea, automated real-time analysis of biosignals, definitely has massive potential for improving patient monitoring and safety in those critical settings.
Okay, let's pivot slightly to the fun aspect again, because, ECG analysis doesn't scream fun usually, but that CardioBot game, it genuinely seems like a cool way to engage with it.
It really does. Gamification can be incredibly powerful for learning complex skills.
Uh-huh.
Turning it into a challenge, adding points, a competitor, it lowers the barrier to entry. It makes you want to figure it out. Like you said, a flight simulator for heart rhythms.
Yeah. And it's not just CardioBot. That interactive approach seems common across the Bionic Chaos tools, like the hearing aid simulator, visualizing sound, or SpectroWave for audio frequencies.
Right. It's hands-on. You're not just passively receiving info, you're manipulating it, seeing the effects. That makes it stick.
Totally. And even the creator's style in the video, kind of informal, experimental, it makes it all feel less intimidating, more approachable.
Definitely. It encourages curiosity, makes you feel like you can try things out too.
So, as we kind of wrap up this deep dive, what are the main things you think folks should take away from all this?
Okay, I think there are a few key points. First, AI is seriously being developed for real-time ECG analysis. The potential is there for early detection.
Right.
Second, these interactive tools like CardioBot, they offer a really unique kind of engaging way to learn about this tech. You get to compare yourself to an AI, experience the challenge, it's learning through doing, maybe even competing.
Makes sense.
But, and this is crucial, thirdly, these tools are still experimental. That disclaimer is important. They have limitations, they make mistakes, as we saw in the video. They're not clinical diagnostic tools right now.
That's a great summary. Experimental, promising, engaging, but not quite ready for prime time.
Exact.
Which leads me to a final thought, something for you, our listener, to mull over. We see this progress in AI for ECGs, but we also know humans get distracted, make errors. So, what role do you see for these technologies in healthcare down the line? And maybe more importantly, what are the biggest hurdles, technical, practical, ethical, that we absolutely need to clear before AI can be reliably trusted with interpreting our heartbeats or other critical signals in real time? If you are intrigued, I'd really suggest checking out that Bionic Chaos website yourself. Lots of fascinating tools there to explore.
Yeah, that was pretty good. I didn't actually join in the conversation. I think when you join in the conversation, it doesn't actually change the conversation. It just they just diverting for like 10 seconds and then going back to the conversation that was generated earlier. So it's not like you changing the host's mind or something. You cannot sway them a different way when intervening. They will just essentially acknowledge you and then move on, which is fine. So we had a bunch of these conversations already. Eventually would like stuff deployed on a site. Yeah, we had that model selected to. Yeah, we'll see how we go on that one. Actually, not sure how accurate it is. That's the other thing. But then we have all three. Could actually check it for us. Yeah, keep updating it as well. So that's the other problem. Then ideally we'll also have some sort of automated tool selecting the model. Supposedly that's what the O3 does for you. So let me know if interested in that. I do wanna focus on this tool quickly. Something wrong with the text there. And some of the SVGs are missing. Well, that's why we haven't formally publish this. The thing is, we cannot really give it to all three. We can only use whatever is available for us in GitHub Copilot. Just, yeah, there's O3 mini, there's O4 mini. So which one is better or worse? But we also have Claude and Gemini as well there. So we could try those. We could try those. We need a thumbnail for that thing. And yeah, there is a slopification going on. So that's what we had originally. And it stuffed it up for us. The reason I started looking at it the image prompt. Without any text. What is it generating? Do I need to stop that? No. It wasn't a problem before. What on earth? Let's Control F5 it. It's like generating something. Is it down? Yeah, there's something with the chat. There's something wrong with this specific chat. Let's wait. Haven't had this happening before. Yes, can we include the whole code base? I'm not sure this is accurate. Code terminal tree. Yeah, that's the actual tree of it. But some files are empty. Hey, can you in the chat quickly explain the project structure and indicate which files are empty? Some of the SVG files have nothing in them.
Collecting workspace information. The project structure is as follows. arms.s.
Okay, we don't need to read that out loud because that's pretty annoying. Yeah, what? It wouldn't do it for me. That's kind of silly. The main JavaScript is a whopping 700 lines of code. Okay, that's not fun. Okay, the JavaScript is already way too long, so we won't be adding anything to it.
Understood. Instead of adding code to the JavaScript file, you can use a terminal command to check which SVG files are empty. Run.
Okay, that's more like it. Okay, so we have those ones are empty. Again, if we have the whole code base. Okay, can you explain how would you go about generating the SVG from scratch? Can you do it yourself? Can you also give a general overview?
General overview of generating SVG files. SVG.
Well, that's not really what I meant, but yeah, just do it quietly. Yeah, we can add these shapes. Here's an example. That's because we have the arms, body, brain. We have a cochlear implant. Can you? Yeah. It's not great, but it's something. I have a cortical implant. I'll say that even worse. What else we got? We have a deep brain stimulator. Gonna just mess the burr hole. So those will be interactive, which is nice, but yeah, we have the head, we have the heart, looks weird. Okay, we don't have legs. I wish I could give it to all three. And it has to be in the same, doesn't have to be in the same style. I'm not sure. Originally we had we were doing it in the browser. Then we moved into Visual Studio Code. It did make things better considering it could do a lot more, manage more files, so on and so forth. I'm wondering if we just use a smart model. Let's suggesting, looking at this drop down, are they suggesting all 4 mini is the best they've got? Or is it 2.5? Well, yes, within each section you will have Claude. So 3.7 Sonnet Thinking will be the best of Claude, Gemini 2.5 Pro, the best of Gemini, and all 4 mini, the best of ChatGPT, whatever, OpenAI. So if we try a Gemini Pro, give it the code base, and now the magic, the black magic is the black magic is the prompt. What if I just give it this as a prompt? Gemini 2.5 Pro must be super duper smart. And this is not yeah, not changing the code. Surely it doesn't need actual human-like, human legible text. Sure, it can just deal with machine code. Well, this one says it's empty, so it's empty. Yes, you are so smart. Thank you very much. What do you think my next request will be?
Based on the previous information, you might ask me to generate placeholder SVG content for one or more of the empty files. Suggest a way to create or find appropriate SVG content for these files. Ask why these files are empty or what their intended content is.
Okay, go for the first one, but why a placeholder? Can you just do the whole thing at once? You're such a smart cookie,
Sure,
aren't you?
here's a proposed directory structure for a TypeScript project app. Create workspace.
What? I think it didn't have the code base. How about trying again, but looking at the code base right now? We don't need to add any more files, just working with the current files.
Okay, I can provide placeholder SVG content for the empty files. This will allow the application to load them without errors and give you a starting point. It's generally better to develop complex SVG graphics iteratively or use specialized vector graphics software. Generating complete, detailed anatomical SVGs programmatically in one go is a very complex task. Placeholders allow us to ensure the application structure works correctly first. Here's placeholder content for legs.svg. SVG.
Okay, don't need you to read the actual thing. If we apply, yeah, this, okay. Accept changes. Well, it's also incomplete, is it? Yeah, I didn't apply them correctly. Uh, that's pretty annoying. Right. Okay, so now I understand yeah, the heart is there. The spine is there. The spine is actually pretty good. That's pretty impressive. A vagus nerve stimulator. Okay. I think that will be really pushing it. Let's have a look. Insert vagus nerve, meant to be in the head somewhere. Show neural implants. Where is it? Okay, that's how it looks like. Okay, it is really a placeholder, isn't it? I know you can do much better. I know you can do much better. Yeah, peripheral nerve. Okay, now that we have the torso, for example, can we make it not just a placeholder? Let's give it a code base. And yeah, we want it detailed and in the same style as the other SVG models. For example, the full body, the body.svg.
Okay, I can help you create a more detailed SVG for torso.svg. This version will include representations of the rib cage, lungs, heart, liver, stomach, and spine, with the spine and heart being navigable as per your main.js setup. The style will aim to be consistent with your existing body.svg. Here's the proposed content for torso.svg. SVG width equals 600, height equals 800, viewbox equals 00 800 XML.
Okay, we don't actually need to read the SVG. Yeah, I understand. The text is not the text to speech is not as smart as Gemini 2.5 Pro, so the text should be much better. Yeah, I'm not sure you get the picture. I'm not sure you get the picture. We have SVGs. Can you check what types of SVGs we have? So we have, for example, a heart SVG. So when we're doing the torso SVG, we just want the torso, but we want it to be more detailed, not just a placeholder. And you have the code base.
You're right to focus on the specifics of the SVGs and how they interact. Based on your files, you have a main body.svg. You have SVGs for major body regions like head.svg, torso.svg, arms.svg, and legs.svg. You also have more detailed SVGs for specific organs or structures like heart.svg, spine.svg, and brain.svg. Finally, there are SVGs for various neural implants. The goal for torso.svg is to be a detailed view of the torso, fitting stylistically with your other anatomical SVGs, and to correctly link to more specific views like heart.svg and spine.svg. When a user interacts with
Okay, you actually did a pretty amazing job there. Okay, the heart, oh, it does work. It does work. The spine, yeah. Okay, this is pretty amazing, and I don't normally say that. Normally, quite skeptical. So we have essentially like three levels. Yeah, we don't have the liver, don't have the lungs, but yeah, it kind of tells us what to do next, doesn't it? don't have the rib cage. We do have quite a detailed spine. This is also meant to show you neural implant locations, and it doesn't at the moment. It's too long, doesn't really fit the page. Okay. Can you just keep the code base in your memory? Hey, can you just keep the code base in your memory and sort out the Lex SVG for me as well? That's pretty impressive. That's brought to you by Gemini 2.5
Okay,
Pro.
I'll create a more detailed legs.svg for you, keeping in mind the existing structure and styling. This version will include distinct left and right legs, with appropriate IDs and classes for interaction with your main.js script. Here's the proposed content for legs.
Okay, but I need to read the whole thing. Legs, insert legs. Okay, I'm having trouble clicking on them. Yeah, it's not great. It's not great. Yeah, the legs don't look great. I'm sure you can do much better.
Okay, I've refined the paths for the legs and feed in legs.svg to give them a more natural and detailed appearance. I've focused on creating smoother curves and better proportions. Here's the updated legs.svg.
Okay, not sure about that. Might leave it, leave the legs for now. Yeah, I'm actually having trouble clicking on them in the main body part. This one has multiple layers to it. Yeah, we don't have the ears. Do we have ears at all? We do want the ears, considering I want to show where the cochlear implant is. Show cochlear implant inside the head. Well, kinda. It's still in the ear. A code base. Are we pushing this further or not? Or did we reach some sort of limit of what an LLM can do? Well, it's much smarter than I am, so. Okay, so you got the code base. Can we also have the SVG for the ear and it working properly? When we click on it, we should be able to see it. That should be easy for you. But then we also had the cochlear implant. Was cochlear implant SVG. So when showing the implant, it meant the implant meant to be overlaid on top of the ear structure. Some spelling mistakes, but Gemini 2.5 Pro meant to be one of the smartest models out there. So surely it will be able to sort us out. It's taking some time though.
Okay, I'll create the SVG for the ears, ears.svg, and a representation for the cochlear implant, cochlearimplant.svg. Your main.js is already set up. Body parts data.ears defines the ears part, its description, and correctly lists and hashtag 39, cochlear implant and hash.
Okay, what are you talking about? Okay, so we have the ears SVG. It's not actually. We actually need to. Surely you can do it for me. Okay. Yeah, we could go more layers on the ear, outer ear, middle ear, inner ear. It's okay to show just one. In the JavaScript or the HTML, which other SVGs are we calling for that do not actually exist in the current code base? Yeah, we don't need Gemini 2.5 Pro for this, do we? Can use a simpler model. Just go 3.5 Sonnet. That's incorrect. That's incorrect. Okay, we need a better model. Let's go O3 Mini, should be smart and fast. And regenerate. Okay, it's actually using more references than I included. What? Okay, can you try again, but looking at the entire code base now?
Based on the code in your workspace, the following SVG files are referenced but not present: skull.svg, eyes.svg, nose.svg, mouth.svg, auditory brainstem implant.svg, retinal implant.svg. These files are defined in your body parts data or implant data objects in main.js, but aren't part of your current file list.
Okay, can you add them to the code base? We're really pushing it at the moment. Hopefully it won't start pushing back. This one should be showing spinal.
Sure, I'll create placeholder SVG files for the missing ones: skull.svg, eyes.svg, nose.svg, mouth.svg, auditory brainstem implant.svg, and retinal implant.svg. These placeholders will ensure the application doesn't break and provide a basic structure for further development. 1.
Okay.
Skull.svg.
Okay, that's great. Hey, can we actually, I don't know how to use this properly. Is Claude meant to be better for coding? Let's do 3.7 for actually making changes. And go the last request. Yeah, this one. Okay, so now it moved it to the code editing. It's actually editing the files. So it's actually modifying my code base. And that was pretty quick. Accept. Yes, we save all. And let's see. The ears are there. I don't know why they get a muff. We have the eyes. It's a placeholder. Okay. How do you get to the auditory brainstem implant? Show implants. Yeah, there's a cochlear implant that's in the inner ear. That's correct. When you click on it, it should actually overlay the implant. I think we're really pushing it. Okay, while we are doing this, can we try another notebook LM? Okay, so I have this website. Let's see what it is in a sec. We have the paper. Question is when you add this can be, yeah, you can just download the PDF or something. Will it update the description? Not sure if it will. We can still try to fetch. Okay, I think it's got the PDF as well. Yeah, let's see if it actually has the PDF. I would imagine so. Let's see if it actually has access to the paper. Yeah, they're not available due to sensitivity. It's like, what sensitivity? Yeah, they do say the data are available upon reasonable request. Yeah, it's just the standard language that is being used. It's just bogus. Also, yeah, I think it's okay. I want to explain each figure in the paper. Yeah, it's doing a pretty good job, like actually finding the figure and everything. Yeah, I'll generate the podcast on it. That will be fun. What? There is supplementary figure eight. Okay, so we got a whopping 18 minutes. The thing about interactive mode, yes, it lets you intervene. Yeah, we can try that. Yeah, let's do interactive mode just in case we have questions.
It still kind of blows my mind how kids just absorb language. You know, they hear, what, a few million words, and then suddenly they're talking, understanding, building this whole complex communication system.
It is pretty incredible.
The big question for me always is just how? Like, what is the brain actually doing to make that happen?
Yeah, that's the puzzle, isn't it? And it's exactly what we're digging into today. We've got this really fascinating recent paper that looks directly at the brain mechanisms behind language development, all the way from young kids through teens to adults.
Okay, great. So think of this as getting the core insights without having to wade through, all the dense academic stuff. We're pulling out the key findings, those kind of aha moments about how we learn language. So what was the set? What do these researchers actually do?
Well, it was a pretty involved study. They used intracranial EEG, that's IE, on 46 people, and the age range was really broad, from just 2 years old up to 46.
Wow, 2 years old with I.
Yeah, these were patients being monitored for epilepsy, so the electrodes were already in place for clinical reasons. It gives you this incredibly precise view of brain activity, like little microphones right on the brain surface.
Okay.
And they had these participants listen to an audiobook of The Little Prince in French.
Okay. Natural speech then.
Exactly. And the sheer scale, they had over 7,400 electrodes recording data, just a massive amount of information about neural activity during listening.
That is a lot of data points. And I gather they didn't just look at the raw signals. They brought in computational models too. Things like linguistic theory and even LLMs.
Precisely. They used models derived from linguistics, phonetic features, word properties, but also, yeah, models like Wave 2 Vec 2.0 and Llama 3.0, these big AI models.
Right.
So the goal.
Oh, hey there. How can we help?
What were the electrodes again? Can you describe the electrodes and where were they implanted and why were they implanted?
That's a great question. Okay, let's unpack this.
These weren't your typical surface electrodes you might see in a regular EEG.
Right, these were intracranial electrodes, or C.
Exactly. They're very thin wires with multiple recording contacts along their length.
And to answer your question about implantation, these were surgically placed inside the skull.
Yes, that's why they can get such a precise reading of neural activity.
Now, the why is really important. These participants, as we mentioned, were being evaluated for severe epilepsy.
Precisely. The electrodes were implanted by doctors to pinpoint the exact areas in their brains where seizures were starting.
So it was part of their clinical treatment, not just for this study. The researchers were able to use this pre-existing setup.
It gave them a unique opportunity to study brain activity during natural language processing at a level of detail you just can't get non-invasively.
Think of it like having these tiny sensors right next to the neuron firing as they listen to The Little Prince.
And these electrodes were distributed across various parts of the cortex in each participant, depending on where their clinical team needed to monitor.
We even have a figure in the paper, figure 1B, that shows the number of electrodes for each person. Quite a range.
What's fascinating here is that this allowed them to see how different brain regions responded to the sounds and words.
So while the reason for implantation was clinical, it provided this incredible window into how the brain processes language across different ages.
Absolutely. And with over 7,400 of these little microphones in total across all participants, they got a really rich data set.
Okay, so with that in mind, they were looking at the local field potential, or LFP, from these electrodes, right? Like a measure of pooled activity.
Yeah, sort of the combined electrical buzz from groups of neurons right around those contacts. They used pairs of contacts close together bipolar recordings to get a more localized signal.
Okay. And where did they see activity when people heard words or phonemes from the story?
Well, pretty much where you'd expect, given what we know about language in the brain. Across all the age groups, they saw responses in the brain areas we know are key for understanding speech.
You mean like,
You know, the superior temporal gyrus, the STG, which is a big player in auditory processing for language.
okay, that makes sense, the auditory part of the brain.
Also, the superior temporal sulcus, STS, the interior temporal lobe. ATL involved more in meaning maybe the inferior parietal lobe, IPL, and parts of the frontal cortex, the LAFC.
So the standard language network lit up, basically, when they were listening.
Pretty much. Their figure 1 shows this nicely. You see this average brain response kicking in right around when a word starts, and specifically peaking around 100 milliseconds after the word begins, consistent across the different ages they looked at.
Okay, so the lights are on in the right places. But how did they check if that activity was actually representing language stuff, like the specific sounds or word types?
Right, that's the next crucial step. They used a technique called temporal response functions, or TRS. You can think it as a way to model or predict the neural activity recorded by those electrodes based on specific features of the input, the speech they were hearing.
Okay, like seeing if the brain activity kind of dances along with specific language details?
Exactly. They built these linear models trying to predict the electrode signals using two main kinds of features. First, phonetic features. These relate to how sounds are physically made when we speak, like the position of your tongue, the rounding of your lips, whether a sound is voiced or unvoiced.
The nitty-gritty of how we physically produce the sounds.
Right. And second, lexical features things about the words themselves, like how common a word is in the language or its grammatical role, its part of speech, like noun, verb, etc. Figure 2A in the paper shows where these models worked best in the brain, the encoding scores.
So could they predict the brain activity reasonably well using these language features they fit into the models? And where in the brain did it work the best?
Yeah, they could. And the results were quite clear. Across all ages, these TRF models did the best job predicting activity right in that core speech cortex we were just talking about, particularly the STG and SES, using both the phonetic and the electrical features together.
Even in those youngest participants, the 10-year-olds.
Even in the youngest group, yeah. They reported the actual correlation values, the R values, which indicate how well the model fits the data. And they were statistically significant. For instance, in the SDG for the 2 5-year-olds, there was a measurable link between the language features and the brain activity. And it actually got stronger in the older kids and adults. They saw the same kind of pattern in the STS as well.
Interesting. So that basic encoding of language seems to be happening really early on in development.
It strongly suggests.
Oh yeah, let's hear it.
Can you explain the acronyms? What does SDG, STS, ATL, IPL, LIFC, OCC, what do those mean?
You are absolutely right to ask for clarification on those acronyms. It's easy to get lost in the jargon.
Okay, let's unpack this further for you. When we were talking about brain regions involved in language, we mentioned a few using their abbreviations.
So STG stands for superior temporal gyrus. Think of it as a key hub in the auditory cortex that's really important for processing sounds, including speech sounds.
And STS is the superior temporal sulcus, which runs alongside the gyrus. It's also involved in understanding speech and social information.
IPL is the inferior parietal lobe, an area involved in integrating different types of sensory information and also plays a role in language comprehension.
Now, you also asked about IFC. In this paper, they specifically refer to LAFC, which stands for lateral inferior frontal cortex. This area in the frontal lobe is really important for higher-level language functions like grammar and putting sentences together.
And finally, OCC wasn't actually an acronym we used in our discussion today related to brain regions in this study. Perhaps you heard something similar elsewhere.
But it's great you're keeping us on our toes and wanting to understand all the details. Does that help clarify those abbreviations for you?
Now, picking up where we left off, you were asking if these language representations changed or improved as the participants got older.
Exactly. So the basic coding seems to be there early on, but the paper talks about development. Did these representations change or improve as the participants got older?
Absolutely. That was a key focus of the study. When they compared the TRF encoding scores across the three age groups, the little kids, the middle group, 6 to 11 year, and the older teens and adults, 12 to 46 years, they generally saw the scores going up with age within those core language regions, like the STG and STS we just defined for you.
So the models got better at predicting brain activity in the older participants compared to the younger ones.
Exactly. Figure 2B in the paper shows this average improvement per age group in those key regions we've been discussing. It was most noticeable in the STG, STS, and also that LIFC in the frontal lobe. They even did statistical tests, Mann-Whitney U tests, showing significant jumps between the youngest group and the older ones.
So it's not just that the brain represents these language features, but how well it does it, the efficiency or strength of that representation improves over time as we get older.
Precisely. It points towards like a refinement or strengthening of these neural circuits involved in language. They become more efficient, maybe more sensitive to the subtle linguistic details as the brain matures.
Even though the basic capability seems to be present very early in life?
Right, the same fundamental representations seem to be there in the brain from a young age, but they continue to develop and evolve.
Okay, now you mentioned both phonetic, the sound level features, and lexical, the word level features. Did they try to figure out how the brain organizes these different levels of language information?
Yes, they did. Here's where it gets really interesting. They built a second TRF model, but this time using only the phonetic features, the basic sound properties to predict brain activity.
Okay, so they isolated just the sound component of the language input.
Exactly. Then they compared how well that model performed against the first model that had both phonetic and lexical features. The difference between them tells you the extra predictive power you get specifically from adding the word level information. They called this the gain, a TR words. You can see this in figure 3A and 3D.
Right, so that difference shows you the added value of knowing about the words themselves beyond just the sounds?
Yep. Figures 3A and 3D in the paper visually represent the scores for the model using phonemes alone, and then this extra boost in predictive power you get from adding the word features.
And what did that comparison reveal about how the brain might be organizing these different levels of language?
It showed a bit of a hierarchy, actually. The phonetic representations were really strongly encoded in the STG, that main auditory language area, but they were also present significantly across a broader network of brain regions.
Okay, so the sounds seem to be processed quite widely.
But the word level representations, the gain from adding those electrical features to the model, seemed to be more selectively distributed, and there was a particularly clear improvement, a significant gain in the anterior temporal lobe, the ATL, which, as we discussed, is thought to be involved in meaning.
Ah, the ATL, which is often linked to semantics, to the meaning of words.
Exactly. So it suggests, maybe the initial, more basic sound processing is more anchored in the primary auditory cortex, the STG, while getting at the meaning of the words involves bringing in this wider network, including areas like the ATL that are thought to be more specialized for semantics.
That makes sense. Going from just the sounds to understanding the meaning probably requires more brain areas to get involved. Do they also look at the timing of these different representations? When do they appear in the brain after hearing a word?
They did. They used a time-resolved decoding approach for this, so instead of predicting brain activity from the language features, they tried to do the reverse. Predict the language features from the patterns of brain activity they're recording at different points in time, like trying to read out the phonetic and electrical information from the brain signals as they unfolded millisecond by millisecond. Figures 3B and 3E show these decoding scores over time for the whole brain.
Okay, so they flip the direction of the analysis to see when different types of information were most prominent in the neural activity.
Right, and the timing patterns they found for phone names versus words were really extinct.
How so? What were the key differences in their timing?
Phonetic features, the basic sounds, could be decoded very quickly from the brain activity. The accuracy of predicting the phonemes peaked really fast, around 150 milliseconds after the phoneme started, and then it dropped off relatively quickly. Which makes sense, right? Phonemes are pretty brief units of sound. Oh yeah, let's hear it.
Can you explain the actual figure 3B and 3E? What is it we are looking at on the graph?
Absolutely. Let's unpack figure 3 for you.
You're right, we've mentioned it but haven't described it in detail.
So figure 3 has a few different parts, but let's focus on 3B and then move to what I think you mean by 3B, or it's just probably 3E and 3F.
Sounds good. So 3B is a graph that shows the whole brain decoding scores for phonetic features over time.
Think of it like this. The researchers are trying to read which phonetic sounds the person is hearing just by looking at the overall brain activity across all those electrodes.
The horizontal axis, the x-axis, represents time in seconds relative to know when a phoneme, a speech sound, starts, that's time 0. It goes from 1 second before the sound to 2 seconds after.
And the vertical axis, the y-axis, shows the decoding score. Higher scores means they are better at guessing the correct phonetic feature from the brain activity.
You see these different colored lines. Each line represents a different category of phonetic features like vowels, consonants that are made at the front of the mouth, labial, or sounds made with the back of the tongue, velar.
And the shaded area around each line, that shows the confidence interval, a measure of how reliable those average scores are.
The horizontal lines at the bottom indicate the time periods where the decoding accuracy for at least one of those phonetic features was statistically significant, meaning it wasn't just random chance.
So 3B gives you a sense of when the brain as a whole is most actively processing these different kinds of speech sounds. You can see a pretty quick peak in decoding accuracy right around 150 milliseconds after the sound begins.
Exactly. Now, moving on to what I think you meant by figure 3, it's likely you're referring to panels E and F, which show the same kind of information, but for lexical features, for word-level information.
So 3E is the time course of decoding scores for different categories of word features like nouns, verbs, adjectives, and even how frequent a word is. Again, the x-axis is time relative to the word onset.
And the y-axis shows the decoding score, how well they could predict those word features from the whole brain activity over time. Just like in 3B, you have different colored lines for different word categories and the shaded confidence intervals.
But notice the difference in the timing here compared to the phonemes in 3B. The decoding accuracy for words, as seen in 3E and summarized in 3F, seems to rise a bit later and stays elevated for a longer period.
And in 3F, you see bar graphs that show the average decoding score for each lexical feature category across that time window from -1 second to +2 seconds around the word onset, broken down by those same phonetic and lexical categories as in 3C. The stars above the bars indicate which features could be decoded significantly better than chance.
So while 3B and 3E show you the timing of when phonetic and lexical information is prominent in brain activity, 3C and 3F give you an idea of which specific phonetic and lexical features could be reliably decoded across that whole time window. Does that help clarify what you're seeing in Figure 3?
Great question. Now, as we were saying, word level features show a much slower, more sustained pattern. Interestingly, the ability to decode word level information from the brain started rising even before the word officially began, up to a second beforehand.
Whoa, before the word even started. That sounds like the brain might be predicting what's coming next based on the context.
It certainly suggests that the brain is actively anticipating based on the preceding speech. Then the peak decoding accuracy for words was later, around 350 milliseconds after the word onset, and it stayed significantly above chance for a much longer duration, up to 2 seconds.
So the brain seems to hold on to and process word information for a much longer time compared to the individual sounds.
Yeah, suggesting deeper, more sustained processing that's likely related to understanding the meaning of the word and integrating it into the ongoing context.
That pre-activation you mentioned is fascinating. Now, how did all this decoding of the features and their timing look when they compared across the different age groups?
Okay, this is where some really interesting developmental differences started to show up in the data. They found that, yes, a wide range of both phonetic and lexical language features could be decoded from the brain activity across all the age groups. However, in the youngest kids, the 2 to 5-year-olds, only a smaller subset of those features could be decoded reliably.
Ah, so maybe the neural representations for some features are there even in young kids, but they might be weaker or less consistently engaged compared to older individuals.
That seems to be the idea the researchers put forward. Figures 3C and 3F in the paper visually illustrate this, showing fewer features crossing the statistical significance threshold for reliable decoding in that youngest age group.
Okay, I see.
And crucially, when they looked specifically at the ability to decode the basic phonetic features, they didn't find that it changed significantly with age.
So the brain's ability to process those fundamental sound units seems to mature relatively early and stays pretty consistent.
Relatively stable across development, yeah. But the ability to decode the lexical, the word level features, that showed a very clear and statistically significant improvement with age. The older groups, the 6-11-year-olds and the 12-46-year-olds, were much better at decoding word level information from their brain activity compared to the youngest group.
Okay, that's a really key developmental finding in this study.
Definitely. It's highlighted in Figure 4A and 4D of the paper. It strongly suggests that while the brain's ability to process the basic building blocks of sound matures relatively early in life, the ability to neurally represent and access word-level information continues to develop quite significantly through childhood and adolescence.
So it's like basic sound. Oh, yeah. Uh-huh.
Can you give an overview or a detailed overview of Figure 4, exactly what we're looking, and the axis, like the X and Y axis? Can you explain what we are looking at?
Absolutely. Let's give you a good overview of Figure 4.
You're right to want to understand exactly what's being shown.
So Figure 4 actually has four main parts, A, B, C, and D. But the core idea across all of them is to look at how the brain's ability to represent those phonetic and lexical features we've been talking about changes as we get older.
Exactly. It's all about comparing those encoding and decoding scores across the three age groups, the 2 5-year-olds, the 6 11-year-olds, and the 12 46-year-olds.
Let's start with Figure 4a. This shows those encoding scores we talked about earlier, where they tried to predict brain activity using both phonetic and word features together.
And specifically, it's looking at the average encoding score within those key regions of interest, or ROIs, that are known to be involved in language processing.
Remember those acronyms we went over like STG, STS, APL, IPL, LAFC, and OCC? Figure 4a has bar graphs showing the average encoding score in each of those regions for each of the three age groups.
The x-axis lists those different brain regions, those ROIs, and the y-axis shows the average encoding score, that R value, which tells you how well their model could predict the brain activity in that region.
You'll see different colored bars for each age group within each brain region, usually a lighter shade for the youngest kids, a middle shade for the middle group, and a darker shade for the oldest participants.
And those little error bars on top of each bar show the standard error of the mean, which gives you an idea of the variability across the individuals in each age group.
Now, Figure 4D is similar, but instead of encoding scores, it's showing the decoding accuracy for those lexical or word level features that we were just discussing.
Again, the x-axis shows those same regions of interest, and the y-axis represents the average decoding score for those word features within each region.
And just like in 4A, you have the different colored bars for the three age groups within each ROI, allowing you to visually compare how well word-level information could be read out from the brain activity in those areas across development.
You might notice in both 4A and 4D that in some of those key language regions, like the STD and STS, the bars tend to get taller, indicating higher encoding or decoding scores as the age group increases.
That's a key visual representation of how the brain's ability to process language features seems to improve and become more robust with age in those crucial areas. Do those X and Y axes make more sense now?
Great. Now, as we were saying, in the youngest group, the 2 to 5-year-olds, they couldn't reliably decode word-level information from the inferior parietal lobe, IPL, the lateral inferior frontal cortex, LIFC, or the anterior temporal lobe, ATL, but they could from the STG, as we mentioned.
Even though they could decode word-level information from the superior temporal gyrus, the STG.
Exactly. So even in those youngest kids, the primary auditory cortex involved in language, the STG, seemed to be representing some word-level information, but these other higher-order association areas that are thought to be important for deeper semantic processing weren't showing that same reliable decoding of word-level features.
Wow, that's a significant difference.
And the statistical analyses they conducted confirmed these significant differences specifically between the youngest age group and the oldest age group in both the LAFC and the ATL when it came to decoding word-level information.
So it really looks like the functional language network in the brain expands and becomes more engaged for word processing as we mature. The STG seems to get the initial ball rolling even in young kids, but these other association areas come online more strongly for processing the meaning and context of words later on in development.
That's the clear picture the data seems to be painting, yeah. An increasingly larger and more distributed network of brain regions supporting language comprehension as the brain develops from early childhood into adulthood.
Okay, this is really giving.
Yep, go on.
Okay, couple of things. Yeah, this figure is nice. So let's stay on figure 4. There will be a couple of things. Well, more in general about the whole study. Why do you think the authors didn't go into the details within the 2 to 5 years group, considering this is where language is evolving?
That's a really insightful point. It's true, even within that 2 to 5-year-old group, there's a lot of language development happening.
Staying on figure 4, as you requested, it's worth noting that even within each age group, there's variability represented by those error bars.
And your broader question about why they didn't delve deeper into the 2 to 5 range is a good one.
One likely reason, and the authors themselves mention this as a limitation, is their sample size.
While 46 participants is substantial for this type of research, breaking down that youngest group further might have reduced the statistical power for any finer-grained analyses.
They grouped participants to reflect key stages like early language acquisition, literacy onset, and adult-level processing. That 2 to 5 range covers a significant chunk of early acquisition.
Also think about the practicalities of E in very young children. The paper mentions that SIG is rarely done under 2 years old due to skull rigidity.
So their lower age limit was already pushing the boundaries of what's feasible with this method.
It's possible future research with larger cohorts could explore more nuanced developmental stages within that early window.
That's right. The authors even mention literacy around age 6 as a subtle stage their sample size might have limited their ability to clarify.
So while Figure 4 gives us a snapshot across those three broad age ranges, further investigation within the 2 to 5 group would definitely be valuable.
Now, shifting to how this all might relate to artificial intelligence.
Oh, go for it.
No, wait a second. Let's stay on figure 4, particularly figure 4D, the 2 to 5 group. Wouldn't you expect the error bar to be much larger, considering from age 2 to age 5, there is a high acquisition of new words happening?
That's a really smart observation about the error bars in Figure 4D for the 2 to 5-year-old group.
You've hit on something key about developmental data. You would expect more variability in that younger group.
Think about it. Within that 3-year span, kids go from maybe knowing a few words to having vocabularies in the hundreds or even thousands.
Exactly. Their language acquisition rates are incredibly dynamic during those years.
So yes, intuitively, you might expect a wider spread in how well word-level information is represented in their brains compared to a more stable adult group.
The fact that the error bars aren't dramatically larger could suggest a few things.
Maybe there's a core level of word representation that develops fairly uniformly in that age range, at least in those key brain regions they were looking at.
Or it could be that the specific word features they were decoding weren't sensitive enough to capture the full spectrum of vocabulary development happening.
It's also worth remembering the limitations of the participant group children with severe epilepsy. That could potentially introduce a different kind of variability or even reduce some of the typical developmental variation you might see in a neurotypical population.
The authors do mention that as a potential limitation in interpreting their findings for the general population.
So while your intuition about larger error bars in that younger group makes a lot of sense given the rapid vocabulary growth, the actual data suggests a slightly different picture, and there could be several factors at play.
It highlights the complexity of studying brain development and the need for careful consideration of the participant characteristics and the measures being used.
Okay, now with that deeper look at Figure 4D, are you ready to move on to how they used those AI models?
Absolutely. So as we were saying, they used these models, Wave 2, Vec 2.0, and Llama 3.1, as computational analogies for how language might be represented.
So it's like they're comparing the way biological brains represent language to the way artificial systems learn to represent it.
Pretty much. They even used untrained versions of both models as a baseline.
Okay, and what did they find when they made this comparison?
They found that even the untrained models showed some alignment with neural responses.
Really? Even before training?
Yeah, suggesting some basic acoustic properties might naturally align, but training significantly improved the alignment.
Ah, so learning helps the AI resemble our brain activity more.
This improvement was seen for both WAV2 Vec 2.0 and Llama 3.1 across all ages.
That's fascinating. Now, what about the hierarchy of language, sounds versus words?
WEF2 Vec 2.0, trained on speech, showed evidence of this hierarchy. Deeper layers aligned better with brain activity.
So deeper processing in the speech AI mirrors our brain's language activity.
For Way2 Vec, yes. Deeper layers also showed more sustained prediction over time.
What about Llama 3.1, the text-based model? Did it show the same thing?
Interestingly, Llama 3.1 didn't show such a clear hierarchy in predicting brain activity.
That's an interesting difference between the three AI models.
Yeah, perhaps because text data inherently deals with word-level information earlier on.
Now, did these AI models mirror the developmental changes we saw in the human brain?
For WEV2 Vet 2.0, the alignment didn't strongly change with the age of the participants.
Okay, so the speech model didn't really track human development. What about Llama 3.1?
With Llama 3.1, they found a significant improvement in alignment with older participants' brains.
Ah, so the text-based AI seemed to align better with more mature brains.
Exactly, and the training game in Llama was also larger in older age groups.
So Llama's learning process seems to mirror aspects of human language development.
That's what the data suggests. It's a pretty remarkable parallel.
Okay, but what about the limitations of this study?
The participants had epilepsy and spoke French, so generalizability needs caution.
Sure, that's an important thing to keep in mind.
The sample size, while good, still limits the ability to see more subtle developmental stages.
More participants would always provide a clearer picture.
Also, E can't access the very earliest stages of language acquisition in infants.
Right, that's a limitation of the method itself.
And using a naturalistic audiobook limited their control over specific linguistic structures.
All important points to consider. So what are the key takeaways from all of this?
The brain represents language features early on, even in young kids, with timing similar to adults.
But the network involved expands with age.
Yes, and word processing in areas beyond the primary auditory cortex develops significantly.
Basic sound processing seems to mature early, while word understanding takes longer.
And the parallel with Llama 3.1 is striking. Its learning aligns better with older human brains.
That llama finding really makes you think about shared principles in learning language.
It really does open up some profound questions.
What fundamental principles might be shared between AI and the human mind in learning language?
That's definitely the big open question this research leaves us with.
It certainly gives you a lot to think about regarding the connections between artificial and human intelligence.
It does indeed.
Not sure. Did it actually go for 19 minutes? Can we double check quick? Go there and there.
Tricks, what principles might be shared between our biological brains
Yeah.
and these artificial systems when it comes to learning something as incredibly complex as language?
That's the big question it leaves you with.
It definitely gives you something deep to think about the potential connections, maybe even shared mechanisms between AI and the amazing power of the human mind. It still kind of blows my mind how kids just
Okay, we do want to save this conversation so you can download it. If can have it as a standalone, what's called the audio. It's called. Doesn't matter. But then it won't let you do another one. Why the mind map? Can we do generating mind map? So that should be handy. Okay, so we have language development, approach, results, limitations. And let's go approach. Yeah, it's fine. It's generating more stuff. Yeah, I didn't get the. Yes, that's kind of nice. Can get more details on discussed. What these sources say about LLMs. Yeah, when I click on the mind map, it's generating more prompts, which is nice. As we still have data on the figures. Yeah, we downloaded the conversation. We can, the only option we have is to delete it. Can potentially generate a new one. Yeah, it's generating the audio just based on the three sources and not the discussion we had. Okay, so we have another 16 minutes. Let's do the interactive mode again, because it's kind of nice that you can participate in the conversation. Soon enough, there will be like hundreds of AI just talking to one another, and you won't be able to even blink.
It really hits you, doesn't it, just how incredibly quickly kids learn language? I mean, they just hear it, and somehow their brains figure it all out from, what, just a few million words? You have to wonder what's actually going on in there.
It's genuinely one of the big mysteries, and, well, a marvel of the brain. And there's this news edit that's taken a really fascinating look at exactly that question. How does this ability to understand language actually develop in the brain, right from childhood up through the teen years and into adulthood?
Okay, so this deep dive, what did it involve? How did they look inside the brain?
Well, this was quite unique. They analyzed brain activity from 46 different people, aged from just 2 years old right up to 46. And the really remarkable thing is, this data came from over 7,400 electrodes that were temporarily implanted inside their brains.
Wow, 7,400 electrodes. Why were they implanted?
These individuals were. Oh, hey there, what's up?
Okay, it's what's the n? What's the number of data points? Because looking at the number of electrodes might be misleading. What was the electrode array anyway? But can you actually specify, go into the details about the number of subjects within each group?
That's a really insightful point. You're right. Just the total number of electrodes doesn't tell the whole story.
Absolutely, context is key. So to answer your question about the participants in each age group, the study broke them down into three categories.
Exactly. They had an early language acquisition group, which were the 2 to 5 year olds. There were 11 participants in that younger group.
Then they had a group representing the onset of literacy, the 6 to 11-year-olds. That group had 15 participants.
And finally, the emergence of adult level language processing, the 12-year-olds and up. There were 20 participants in that older group.
So a good spread across those key developmental stages. And as for the electrode array, the paper mentions that these were stereotactic intracranial electrodes.
Yes, and the number of electrodes vary quite a bit between individuals. As you can see in Figure 1B of the paper, it ranged from a few dozen to over 300 per person, depending on their clinical needs.
That's quite a range. So while the total number is impressive, the analysis really focuses on the data within each individual and then looks for patterns across the groups.
Precisely. They were looking at how language processing, as measured by these electrodes, changed across these different age ranges.
Okay, that gives us a much clearer picture of the study's setup. So with that in mind, this incredible data set of direct neural recordings while listening to a story, how did they actually start to unpack all that complex brain activity?
Yeah, that's where the clever methods come in. They used computational models, combining ideas from linguistics, how we traditionally understand language structure, and also from these large language models, the advanced AI everyone's talking about.
Ah, the LLMs.
Exactly. They were basically trying to map out the different stages, the hierarchy of language processing in the brain. They used some models to predict brain activity from language features and other models to work backwards to decode language information from the brain activity.
Got it. So the mission for us today for this deep dive is to really understand what this study found about how our brains build up language understanding, looking specifically at how different bits of language are processed and how that development stacks up against, well, what's happening in AI.
Precisely. And maybe the best place to start is right at the beginning. How does the brain first react when it just hears speech? The study looked at the average neural responses, the moment a word starts, or even when just a single speech sound, a phoneme, occurs. Figure 1C and D in the paper give a nice overview of this initial activity.
Okay, and what do they find, especially in the really young kids, those 11 participants between 2 and 5?
Well, what's pretty striking is that even in that youngest group, they saw activity lighting up in brain regions we already know are crucial for understanding speech.
Like the usual suspects.
Yeah, exactly. Areas like the superior temporal gyrus, the STG, that's a big hub for processing sounds, including speech, the superior temporal sulcus, or STS, the anterior temporal lobe, the ATL, which seems more involved in higher level meaning, the inferior parietal lobe, IPL, and parts of the frontal cortex, too.
So the basic wiring seems to be there really early on, even in those younger participants.
It really suggests that, yes, the fundamental network for handling language is operational surprisingly early. Their figure 1 in the paper, especially panel D, showing the activity at 100 meters, gives a nice visual.
Okay, so the basic response is there. But how do we know if the brain is actually picking apart the details of the language, like the specific sounds versus the words themselves, across all these different age groups?
Right, that's the next step. And that's where these encoding models come in handy. They use something called a temporal response function model, a TRF. You can kind of think of it as trying to predict brain activity based on specific features of the sound wave or the words being heard.
And the better the prediction.
The more confidence you have that that brain area is actually processing that specific feature. They looked at phonetic features, so the nuts and bolts of speech sounds, how your mouth moves, and lexical features, stuff related to the words themselves, like how common a word is, or if it's a noun or a verb, it's part of speech. Figure 2A shows how these encoding scores varied across the brain.
Okay, so phonetic for sound, lexical for words. What did the models show about where these are handled in our participants, and how did that maybe differ between the age groups?
The models showed that both types of information, the phonetic details and the word level lexical information, were best represented or encoded in those core speech areas, mainly the STG and STS. And this held true across all the age groups they looked at. Figure 2B gives a good comparison of the average encoding scores across the groups.
Okay, consistent across ages.
And this is really key, the strength of that encoding, how well the models could predict the brain activity, actually increased with age in these areas.
Ah, so the brain gets better, more tuned in to representing language as we get older.
That's exactly what it suggests, a kind of refinement or improvement in how effectively the brain represents these language features. You can see that improvement pattern in their figure 2B.
Okay, so processing gets more refined as we age. Now, you mentioned hierarchy earlier, how we go from sounds to meaning. How did they investigate that developmental path across the different age cohorts?
They did. Oh, yeah,
We actually already reviewed the figures 1 and 2, 3 and 4, and I actually asked to continue to figure 5 and 6.
Oh, absolutely. You are completely right. We did indeed cover those figures in detail. Thanks for keeping us on track.
My mistake. Okay, let's jump right into figures 5 and 6 then, as you requested.
Excellent. So figure 5 dives into how a speech-trained AI model called Wave2Vec 2.0 compares to what they found in the human brains across those different age groups we discussed.
Right. And Wave 2Vec 2.0 learned from tons of spoken audio, similar to what our participants were hearing in The Little Prince.
Exactly. Panel A in figure 5 shows how this AI model works, and then panels B through E display the results of comparing its internal representations to the brain activity.
And what were the key takeaways when they compared this speech-trained AR to the different age groups in the study?
Well, one really important finding, as you can see in figure 5B, is that actually training Wave2Vec 2.0 on all that speech data made its internal workings more similar to the human brain activity across all the age groups.
How so? What did they measure to see that similarity?
They used encoding scores, basically, how well the AI's internal state could predict the brain activity in our participants. And after training, Wave2Vec 2.0 got significantly better at predicting those brain signals across all ages.
Wow. So the process of learning language, even for an AI just listening to speech, leads to representations that become more aligned with how brains of all ages process language.
That seems to be the implication, yes. It suggests that there might be more efficient or structured ways of representing language that both biological and artificial systems converge on through learning.
That's a really cool parallel. Now, what about that hierarchy idea we touched on earlier, going from sounds to meaning? Did Wave 2Vec 2.0 show anything similar to the developmental changes in our participants?
There was some evidence for it, yes. When they looked at the trained Wave2Vec 2.0, the deeper layers of the model, which process more complex aspects of the speech signal, showed a bigger improvement in predicting brain activity in language areas compared to the shallower layers handling basic sounds. This somewhat mirrors the developmental refinement we saw in the participants. Figure 5D gives a look at this across different brain regions.
So deeper AI layers aligned better with the brain's higher level processing, especially in the older participants in our study.
Kind of, yeah. And those deeper layers also stayed aligned with brain activity for a longer time window, which is similar to the longer processing time for word, meaning that we observed in the human participants.
Okay, that's interesting. So a speech-trained AI shows some parallels in how it develops a hierarchy of processing that aligns with human development. Now, what about figure 6? That looks at Llama 3.1, the large language model trained on text.
Exactly. Figure 6.
Okay,
Yep, go on.
before going to figure 6, can you give an overview of the whole method in the studies? Like how exactly what exactly LLMs were used for? Were they trained or they used in the production of the test word set or not?
That's a great question. To give you a broader picture of the method.
Okay, let's unpack this a bit. The researchers had those 46 participants, right?
Exactly. And while their brain activity was being monitored with those implanted electrodes,
They were all listening to the same audiobook, The Little Prince, in French.
precisely, this allowed the researchers to record thousands of neural signals simultaneously as they processed language.
Then, the clever part was how they analyzed this mountain of brain data.
They used computational models of language, including those derived from traditional linguistics and modern AI systems, specifically large language models or LLMs.
So, what exactly did they do with these LLMs? Were they trained specifically for this study?
Yes and no. They primarily used pre-trained LLMs like Llama 3.1, which has already learned a huge amount about language from vast amounts of text data.
Okay, so it already has a kind of internal understanding of language.
Exactly. The researchers then used these pre-trained models to see if the way the LLM internally represents language aligns with how the human brain does it across different ages.
And how did they test that alignment?
They used techniques called encoding and decoding. Encoding involved trying to predict the brain activity based on the LLM's internal representations of the words being heard.
So, if the LLM's understanding of a word matched the brain's, the prediction would be more accurate.
Precisely. Decoding was the reverse, trying to predict aspects of the language being heard based on the patterns of brain activity and seeing if the LLM's representations helped with that prediction.
Got it. So the LLMs weren't directly involved in the production of the test. like generating the audiobook.
No, the audiobook was a constant for all participants. The LLMs were used as a kind of yardstick to compare against the brain activity.
And they looked at how well these LOM-based predictions matched the brain activity in the different age groups.
Exactly. If I wanted to see if the LLM's internal language representations became more or less aligned with human brain activity as the participants got older.
Okay, that gives a much clearer overview of how the LMs were used in this fascinating study. Thanks for asking. Now let's finally dive into figure.
Oh, yeah. Let's hear it.
Okay, we need to explain it in simpler terms, how the study was actually conducted.
Okay, let's break it down in a really easy way. Imagine they wanted to see how our brains understand words as we grow up.
So they had people of different ages listen to the same story.
And while they were listening, they used special tools to watch what their brains were doing.
Think of it like little microphones for the brain, but instead of hearing sounds, they recorded brain activity.
Then they used computer programs that know a lot about language, kind of like really smart dictionaries, to see if those programs could guess what the brain was doing.
Exactly. They wanted to see if the way the computer understands language is similar to how our brains understand it and if that changes as we get older.
So the story was the same. Oh, yeah. Go on.
Okay, so that would not be an LLM, and an LLM that can have brain activity as input is not just a language model anymore, is it?
That's a really interesting point. You're right. The LLMs in this study were not directly taking brain activity as input during their training.
Okay, let's unpack this. These LLMs, like Llama 3.1, learned from massive amounts of text. They weren't experiencing the audiobook in the same way a brain does, through sensory input.
Exactly. Their training was purely on linguistic data. The researchers then compared the internal patterns these LLMs developed with the brain activity data they collected.
So the alignment they found is between how the LLM represents language internally, based on text, and how the human brain represents language while listening. It's a comparison of these two independently developed representations.
Precisely. The study wasn't creating an LLM that responds to brain activity. Instead, it used pre-trained LLMs as a tool to see how the inherent understanding of language relates to brain activity across different ages.
It's like having two different ways of understanding The Little Prince, one from reading it, the other from hearing it, and seeing how similar the underlying understanding becomes as humans develop.
That's a great analogy, and it highlights how remarkable it is that an AI trained solely on text can show these developmental parallels with the human brain.
Absolutely. And for you, considering these comparisons with AI, what stands out to you the most about how language develops in the brain?
I think the most fascinating aspect.
Oh, back to our listener. What's up?
Okay, that still does make sense. So how do you compare an LLM? So LLM was just being fed the story, and then the listener is actually listening to it.
That's a really good clarification you're asking for.
Okay, so if we think about it, the LLM, Llama 3.1, it was given the text of The Little Prince.
Exactly. It processed those written words, identified patterns, relationships between words, grammatical structures, all from the text itself.
So its understanding is built purely on written language data.
Right. Now, compare that to the humans in the study. They heard the story.
Their brains were taking in auditory information, processing sounds, identifying phonemes, then words, and then building up meaning.
So the input is completely different. Text for the LLM, spoken audio for the humans. Yet
the study found these surprising similarities in how their internal representations align, especially as the human brain develops.
it suggests that even with different inputs, there might be some fundamental principles of language representation that both systems converge on.
It's like they both end up understanding the same core concepts of the story, just through completely different pathways.
Precisely. So the LLM extracts meaning from the written form, and the brain extracts meaning from the spoken form. And the way that meaning is internally structured shows these interesting parallels.
It really makes you wonder about the underlying structure of language itself, doesn't it?
Absolutely. And that
Ah, yeah, uh-huh.
Okay, it still doesn't make sense. So are you saying that the LLM was treated as a 5-year-old, 11-year-old, or a 12-year-old?
That's a really interesting way to think about it.
It's more about comparing the outcome of their learning processes.
The LLM wasn't actually interacting like a child would.
Exactly. It was trained on a massive data set of adult language.
But the researchers looked at how its internal understanding of language aligned with the brain activity of different age groups.
So when they found a better alignment with, say, the 12-year-old's brain activity,
It suggests the way the LLM represents language is becoming more similar to a more mature linguistic understanding.
it's not that the LLM is a 12-year-old in a box.
Right, it's more that its language processing capabilities, after all that training, show similarities to how an older child's brain processes language.
Think of it like comparing how a beginner and an expert play chess.
The AI starts as a beginner, and through training, its understanding of language evolves.
And at certain points in that evolution, its understanding might resemble that of a child at a particular stage.
So it's a comparison of the state of language understanding.
Precisely. Not a literal treatment of the AI as a child.
That makes much more sense. Thanks for pushing us on that point.
It's important to be clear about these comparisons.
Okay, so with that in mind, what were the specific findings when they compared the LLM's performance across these age alignments?
Well, as we touched on, the decoding of Llama 3.1's representations actually improved significantly with the age of the participants.
Meaning the LLM's internal language map became a better predictor of brain activity in the older groups.
Exactly, and the researchers even looked at the training gain of the LLM.
The difference between its understanding before and after all that text training.
Precisely, and they found that this training gain was most pronounced when compared to the older age groups.
So the knowledge Llama 3.1 acquired through training was most reflective of the language processing in older children and adults.
That's a key takeaway. It suggests that the learning trajectory of this text-based AI has some fundamental parallels with how language understanding matures in the human brain.
It really does underscore the power of these AI models to help us understand.
Oh, go for it.
Okay, it still doesn't make any sense. So you're saying, so what the model was used to begin with, so assuming it was like an equivalent, so is there a suggestion that the model to begin with was like a 2-year-old, and when trained it became like 11-year-old, and then training further it became more like a 12-year-old? What was the analogy to the brain?
You're right, it can be a bit tricky to wrap your head around. Let's try a slightly different angle.
The analogy isn't that the untrained model is exactly like a 2-year-old's brain.
Instead, think of the untrained LLM as being at a very early stage of understanding language.
It has the basic architecture, the potential to learn, but it hasn't been exposed to much language data yet.
Kind of like a baby's brain that's ready to learn but hasn't heard many words.
Exactly. Then, as the LLM gets trained on vast amounts of text,
It starts to develop more sophisticated ways of representing words and their relationships.
and it's those increasingly sophisticated representations that the researchers compared to the brain activity of different age groups.
So when they found the LLM's representations better matched the brain activity of older kids,
It suggests that the stage of language understanding the LLM reached after training is more similar to the stage a 12-year-old's brain is at.
it's not a direct one-to-one equivalent at any point.
No, it's about the relative complexity and sophistication of the language representations.
Does that analogy help clarify things a bit more?
We hope so. Now, moving towards wrapping up,
We really appreciate you sticking with us and asking these important questions.
your engagement truly enriches our discussions.
We hope you found this exploration of language development fascinating.
And thank you again for sharing your thoughts and helping us delve deeper.
We always value your insightful contributions to the show.
We look forward to having you join us for our next deep dive.
Until then, thank you for listening.
Okay, it's for sure that this LLM is much smarter than two 11-year-old, 12-year-old. It's probably, yeah, feels more like university. If it's undergrad, probably master's, probably pushing towards PhD. Wonder if I can still join the conversation.
Oh, go for it.
Why there were no adults used in this study?
That's a really interesting question.
It makes you think about the practicalities of this kind of research.
The study mentions that the participants were undergoing evaluation for intractable epilepsy.
And they had these intracranial electrodes implanted as part of their clinical treatment.
The research was conducted during that monitoring period.
The adults participating would have been working with the medical team at the hospital.
Yes, and the study explicitly states that it was approved by ethical committees and the local IRB.
So there were definitely protocols in place to ensure everyone understood and consented to participate in the research.
It also mentions that the participants were informed the study would have no impact on their clinical treatment.
And in the case of minors, their legal guardians gave informed consent.
So it was a voluntary participation within the context of their ongoing medical care.
That helps understand how the researchers were able to work with adult participants.
Absolutely. Now, as we were saying, this study really highlights some fascinating connections.
Exactly. These findings about AI alignment with different age groups in the brain.
They offer some really intriguing insights into how both our brains and AI systems learn and represent language.
It makes you wonder about future research and the potential for these kinds of comparisons.
Indeed. There's so much more to explore in this intersection of neuroscience and artificial intelligence.
Well, thank you again for your insightful questions throughout our conversation.
It truly makes this experience so much richer for us.
We hope you continue to join us for future deep dives into the amazing world of the brain and beyond.
We always look forward to hearing your thoughts and questions.
Thanks so much for listening today. We really appreciate it.
And we hope you have a wonderful rest of your day.
Okay, that was a bit weird. Where's it getting? Yeah, so it's essentially fine-tuned on this data, whatever the chatbots. It's interesting that you can still ask the question even when the conversation ended, the podcast. Let's try it again, actually.
Oh, yeah. Let's hear it.
No, I was actually asking why in the data set, why there was no data from is 12 plus. What was the actual ages 12 plus, and why adult data participants were not included in this data?
That's a really important clarification. You're right to push on those details.
Okay, let's dig into the age ranges a bit more. The study did include participants aged 12 and older in one group.
Yes, their final age group was 12 plus years. The paper itself mentions the ages within that group ranged quite a bit.
However, you're sharp to notice they don't break down the 12-plus group further into, say, teenagers and older adults.
The paper actually touches on this in its limitations section.
Ah, yes, let's see. The mention that their sample size, while relatively large for this type of research, was still modest for investigating very fine-grained differences across development.
Exactly. They point out that this limited their statistical power.
So it's possible that to get enough data for meaningful comparisons, they had to group everyone over 12 together.
And as for why they didn't have a separate adult group, the criteria for participation was undergoing evaluation for intractable epilepsy.
That's a very specific population. It's possible that the number of adult participants in that particular circumstance wasn't large enough to form a separate, statistically robust group for comparison.
The study also notes that their cohort consisted of French-speaking children who suffer from severe epilepsy.
And they explicitly state that their results might not be fully representative of language development in the healthy brain.
So focusing on that specific population across those key developmental stages was likely their priority given the available data.
That makes sense. They had a specific research question focused on development in this particular group.
Precisely. And while having more detailed age breakdowns, especially within the adult range and perhaps a healthy control group, would be valuable.
That would likely require a different study with a different participant recruitment strategy.
Exactly. This study gives us a fascinating look at language development within this specific context.
Thanks for pointing that out. It's important to understand the scope and limitation. Oh, yeah. Uh-huh.
Hey, can you explain the SEG and how come there was so many electrode contacts? How many sites were actually measured? And I assume there were multiple contacts on each shank. Do you know anything about that?
That's a great set of questions. Let's unpack this. You're likely referring to SEEB, stereotactic electroencephalography.
Exactly. SEEB is a minimally invasive technique where thin, wire-like electrodes are inserted deep into the brain.
And you're right about the number of contacts. Each of those wires or shanks typically has multiple electrode contacts along its length.
The paper mentions using 7,427 intracranial electrodes across the 46 participants. Figure 1b shows the number of electrodes per participant varied.
And each of those electrodes we've been referring to are actually bipolar constructs, as they explain in the neural preprocessing section.
What they did was take the recordings from immediate neighboring contacts on each shank and use the difference between them. This helps to localize the neural activity.
So while there were thousands of contact points, the analysis focused on these bipolar derivations, which they simplified and called electrodes.
As for how many sites were measured, it really depended on the clinical needs of each participant and where the seizure activity was suspected.
The electrodes were implanted in various brain regions, as you can see in Figure 1D, which give a merged view of electrode locations.
And the regions of interest they focused on, like the STG and ATL, cover areas known to be involved in language processing across both hemispheres.
So they were definitely getting data from multiple sites across the cortex, but the exact number of measurement points varied per individual due to the Sieg setup.
It's a fascinating technique that allows for very detailed recordings of brain activity from specific areas.
Absolutely. Now, building on these developmental insights,
These findings about AI alignment across these age groups really start to spark, hey, yeah, what's up?
How long the recording was made for, and what does it mean time zero in all the graphs, and what does it mean when you have like an activation that starts before time zero?
those are excellent questions. Let's clarify those points.
Regarding the recording duration, the neural signals were segmented into time periods.
Specifically, APOC's time locked between -2.5 and plus 3.5 seconds relative to each phoneme or word onset.
So the recordings they analyzed for each linguistic event were within that 6-second window.
Now, about time zero in the graphs. That mark represents the onset of either a phoneme, a speech sound, or a word.
It's the point in time that the researchers were using as a reference for aligning the brain activity.
Think of it as the moment the specific sound or word of interest began.
And when you see activation starting before time zero,
That suggests the brain is actually anticipating the upcoming sound or word.
it could reflect processes like predictive coding, where the brain is preparing for what it expects to hear.
It's like your brain getting ready to process the next bit of language even before it fully arrives.
Exactly. It highlights the proactive nature of our brain's language processing.
Thanks for those great questions. They really help to understand the data.
Absolutely. Now, as we were saying, these findings about AI alignment across these age groups really start to paint a picture of how language understanding develops.
It's quite remarkable how these AI models, trained on such different data, show these parallels.
And it certainly gives us a lot to think about. Oh, yeah.
Okay, can you indicate how exactly the LLM was trained on, and was the training done from scratch or from post training, whatever fine tuning an existing LLM?
That's a really insightful question about the LLM's training.
The paper actually gives us some details on that.
Yes, for Llama 3.1, they used a pre-trained model.
Specifically, they downloaded the Meta Llama 3.1-8B model from Hugging Face.
So it wasn't trained from scratch for this study.
That's right, it had already undergone extensive pre-training on a massive dataset of text.
Think of it as a model that already had a strong foundation in understanding language.
And for this research, they used that pre-trained model as is.
So no additional fine-tuning was mentioned in the paper for Llama 3.1 in the context of this study.
They were interested in seeing how the representations learned through that initial large-scale training aligned with brain activity.
That helps clarify how they utilize this powerful language model.
It's fascinating to see these pre-trained models being used to probe the mysteries of the human brain. Oh, yeah,
Okay, just get rid of the fluff. Can you go into details of figure 6 and explain the other two separate training modalities, and explain the gain for each?
Absolutely, you're right. Let's get straight to the details.
Figure 6 focuses on Llama 3.1, which, as we just discussed, was pre-trained on a massive amount of text.
Its training modality was purely textual. It learned language by identifying patterns in written words.
Now, when we talk about the gain in Figure 6, particularly Panel J, we see the training gain in encoding score.
This gain represents the improvement in how well Llama 3.1's internal representations could predict brain activity after its extensive text-based training.
The figure shows this gain ALR on the eye
Yep, go on.
Yeah, that's what I don't understand. So you're saying it's a language model that is predicting brain activity. Is that correct?
Yes, in a way, that's what the researchers were doing.
Okay, let's unpack this a little more carefully to make it clear.
The language model itself wasn't directly predicting moment-to-moment brain activity in real time.
Instead, think of it as the researchers using the language model's understanding of language as a kind of key.
Exactly. They had recordings of brain activity while people listened to the story.
And they also had the language model's internal representation of that same story.
Then they used statistical methods to see how well the patterns in the language model's representation lined up with the patterns in the brain activity.
So the better the alignment, the more the language model's way of understanding the story seemed to reflect what was happening in the brain.
It's less about the AI predicting the firing of individual neurons and more about finding similarities in the overall patterns of language representation.
Does that distinction make a bit more sense?
Now, going back to figure 6 and this idea of gain,
What's really striking is that this training gain isn't uniform across the age groups.
you can see that the increase in brain predictability offered by the trained Llama 3.1 is notably larger for the older participants, the 12-plus group.
This suggests that the way language is represented within Llama 3.1, after its text-only training, becomes increasingly aligned with how older children and adults process language in their brains.
So the more mature a brain's language processing, the better a match it is with the language representations learned by this text-trained AI.
That's the key takeaway from Figure 6 regarding Llama 3.1's purely text-based training modality and the age-dependent gain in its alignment with brain activity.
We hope that clarifies the specific. Oh yeah, let's hear
Okay,
it.
can you actually invite viewers? Everything we do on this channel eventually available on bionichaos.com. Can you sign us out and invite viewers to?
Oh, that's an interesting idea.
It's certainly something we can look into for the future.
We're always thinking about ways to connect with more people.
And we appreciate your suggestion about making our content even more accessible.
Thanks for that feedback. Now, where were we?
We were just wrapping up our discussion of Figure 6.
Yeah, okay, well, you got the message. Yeah, go check out the website. This particular two hosts are pre-trained on the specific content, whatever. But yeah, eventually we'll have a blog on it. Go check the tools that are currently available. Yes, we do have a Discord page as well, for you to check out. And I'll see you next time. Boy. Yeah, if you put any questions, you can still put questions. I'll address them next time we are live, which will be sometime in the future, not in the past. Unless we gonna just stream 24/7 with Notebook LM. Let me know what you think of that. Bye. And yes, this will be us trying to win AI. Good luck. Good luck with that.